can you briefly tell us about what Classiq does? I guess partly in plain terms, so that like a smart high schooler could understand it. Um, yeah, we'll
Yeah.
start there.
So Classiq is basically a platform that you can write quantum algorithms, I mean code for quantum computers that will be run on quantum computers, which is generally different than code for classical computers. So Classiq is a platform to write this code in a high function-based level, meaning that you write with function as variables as you do when you code with Python, very similar to Python. And the idea is not to work and think in the quantum circuit level, which is the basic object that you feed to quantum computers, the main object. There are a few other methods, but the main way to talk to a quantum computer. Most of the software today is in the level of quantum circuits. So these basic languages or instructions for a quantum computer, and we wanted to abstract um, above these circuits because they inherently have some problems with them. For example, even writing a simple arithmetic expression like on a quantum computer would take you a lot of gates and would be very cumbersome um, to a coder, and getting the most optimized circuit for like implementing an arithmetic expression is something nearly impossible. I mean, getting some kind of circuit is feasible, but finding the most optimal circuit that uses um, the least number of qubits and is like is with a short depth is something that's really hard to achieve. When I say depth, I mean the number of operations that the qubits undergo. So basically, you measure for resource awareness, you measure it in in two basic ways. It's circuit depth is how many operations do you have like on like the qubit that you have the longest the largest number of operations on, and the total number of qubits you need in the circuit, and you want to minimize both, of course. So Classiq invented a language called QMod that generally lets a user write their quantum code like they do in Python with functions and variables and constructs and not thinking in the circuit level. And we have a synthesis engine which takes your quantum code that you built and you think in the algorithmic level. Like let's say you want to implement arithmetic expression, so you generally write this arithmetic expression. And this is the main part of the code. And then we have a synthesis engine, which is patented. Um, as we know that open source, our synthesis engine and part of our code is not open source, and our GitHub library of algorithms is open source. Um, so we have the synthesis engine, which takes your high-level code and synthesizes it into a quantum circuit and an optimized one. So you can pick your constraints. You can pick if you want it to be like with a maximum number. What's the maximum number of qubits you allow it? What's the maximum number of depth you allow? And what you want to optimize for, if it's depth or width. And you can get your optimized circuit from your high-level code.
Makes sense. I appreciate the thorough response. So I think what my viewers are going to be most interested in is, let's say I have a Python script that runs Doom. Can your code convert Doom into like, gate code?
Oh, that's an interesting question. Quantum computers are not good for everything. Like not good to run graphics on, I guess, like to run, computer games on. But they are good for a couple of different things in the world, or yeah, at least none of them were proven. Maybe only Shor's algorithm and Grover's, which was like proven like speed up over classical methods. But generally, quantum computers can be used to find new drugs, find new medicine, um, and simulating physical systems, of course, because quantum computer will be like naturally simulate quantum systems in nature. And if it's like some kind of statistical, like solving some statistical problems in finance, like let's say simulating some models faster than classical computers. And I guess, you can find it like in optimization, you can also find some benefits not proven yet. But Doom, not sure, but other specific applications. Oh, and then cryptography, of course. Also, like this is a short algorithm generally, like cryptography. So this is one of the main things. But these are the things like the quantum computer can give some benefit over classical computers. It won't be everything, of course.
So you mentioned cryptography and I think chemistry, or at least finding new drugs. Is there a client that you can talk about or an application you can talk about where you guys made an impact?
Yeah, sure. Most of the clients come from the automotive sector or the financial sector. If it's big banks or automotive companies, known automotive companies like BMW, and others. And what we did generally is like in option pricing, which is generally like setting a price for an option, which is something that a bank generally does if they want to sell options for some asset at a strike price at some specific date. And yeah, and options is something in finance. So the banks worked with us to implement quantum algorithms for all kind of different option types. The basic one is European option, so this is not really interesting, but um, more complex types of options like auto-callable options, which are path dependent and have several assets, and options called rainbow options. I think they are only they're path dependent and it's one asset. So we teamed up with Intesa Sao Paulo and we wrote two wonderful algorithms. One of them, the latest one, autocallable options, won second prize in IEEE conference. That was in 2025.
Nice.
And generally with BMW, we've been exploring like cooling systems, like differential equations. Um, so solving like a set of differential equations with a quantum computer. Wrote a nice article about this as well, nice paper about this as well. And generally, as the quantum computers are not mature yet, generally what we do is we explore like new algorithms or like using known algorithms for new applications. I would say it better. And it's generally proofs of concept like, okay, let's so this can be practically implementable with a quantum computer, and when they're good enough, there could be some speed up over classical computers. Of course, this needs to be further researched when we have the computers one day.
You have an estimate of how many qubits or in how many years do you think it'll be, or it could be even months, with the new computers coming out, um, until like it's, better than a regular computer to solve these
Um,
algorithms?
it's a very tough question, and you have people, very, very high-ranked people saying very different answers about this.
It doesn't
If
have to
you
be time, just qubits even.
if you ask my professor, he would say like to have like quantum advantage will take like 15 years if it will happen at all. And if you ask people in the company, we hope it will be less than 5 years. And if you ask, I think an NVIDIA CEO, he will tell you, no, sorry, IBM CEO, he will tell you if everyone works together, it will be in 2 years. And I'm not really sure when it will happen, the advantage.
Yeah, but you're getting ready for it, basically.
Yeah, sure, of course. As we are quantum software, we build ourselves upon like the idea that it will come soon. Because as you know, like okay, there are NISQ. NISQ is this area is noisy intermediate area of quantum computer. So we have some algorithms for today, but of course the quantum advantage was not achieved yet. Advantage meaning you have some meaningful algorithm that really can make some change in the world, and it is important to do something practical. That a quantum computer can run faster than the best classical computer, supercomputer in the world. Um, so this is the definition of quantum advantage. And we're still not there yet. And until we're there, things will be more proof of concepts and theoretical speed ups, pen and paper algorithms with proving speed ups theoretically. But we, of course, plan for the day that will happen and work hard and hope it will happen soon. And as you know, we build our platform is built to write circuits of up to infinity qubits, and we're not hardware aware yet. Oh, we are hardware aware. I'm sorry, but we're not error corrected yet, and we're not fault tolerant yet. That's the word. That's what I want to say. And we are focused on um, implementing the best optimized circuits.
That makes sense. You mentioned hardware aware. Is there like a company, Zurich Instruments, Quantware, Quantum Machines, that you guys are like partnering with or talking to? Because it sounds like you guys kind of write like the software to figure out how the machine should look, but then it seems like you still need to talk to someone else. I mean, not that you're trying to do like the full machine, the full ecosystem, but let's say I was trying to run a whole ecosystem. I would have to talk to a front end developer, and maybe the guy that has the FPGA basically. So I guess get back to my question, is there a particular company that you're working with, or someone that you kind of have a smoother API meshing with? That makes sense.
Yeah, it's a good question because it lets me also correct what I've said before. So we are hardware aware, meaning we are integrated with a lot of hardware providers that we allow you to run on them through our platform, like through the cloud, but tunneling this through our platform, and getting responses from the cloud and doing all the post processing of the measurements in our platform, of course, with our language. Um, and so we have a lot of partnerships going on with a lot of companies like Quantum Machines, for example. We're exploring a lot of different collaborations we can pursue. And generally, all the hardware providers that work with us, so we're fully integrated with them. Um, and we allow to run on them if you have credentials for running on this hardware. Um, but generally we allow this, and we're not error corrected, meaning we can leave error correction to the hardware side, or to other vendors, of course, also exploring this, getting to partnering up with some error correction startup or bigger company that focuses on error correction and surface code, and partnering up with them, and like giving the fuller stack, even though we're, I think, one of the most broad, companies giving the most broad stack of all companies, I guess.
That makes sense. Okay, so yeah, so like you guys write the software, or light someone write the software, I should say, and then that goes over. You can even sounds like you can do it over the cloud. That goes over to someone's, you know, I always don't have like a good name for it. Like I guess accelerator maybe. It's a thing that goes from like digital speed to like quantum speed. Where you need like the gigahertz frequencies to talk to the qubits. And then they can from there they can talk to the qubits to get their response. Do you guys do any software for like analyzing the response? I mean, I guess you wouldn't be analyzing like the pulse response, but maybe converting the pulse response to, like an output, like what it would look like qubit wise.
It's a good question. I think all the hardware providers we work with just generally give us we give them the circuit and they just give us the measurements, the probabilities and the end product of what we send them. I think like everything happens on the hardware side. Maybe I'm mistaken. I'm not very like into the details of this.
No, I think you answered my question in that, that was probably a better way to put it. When they hand you the measurement, that goes into your code, and then you can like interpret the measurement and be like, this experiment was successful, or I did factor the number, basically. Does that make sense?
Yeah, so generally what you do in quantum computing, let's say even if you run on a simulator, we have simulators that are Classiq simulators as well, that can run up to 28 qubits that you can use free of charge if you have some academic email and you from the North Americas, most of Europe now as well. So you can register free of charge and use our Classiq simulator for tw up to 28 qubit as much as you like. And generally what happens is like with hardware, with simulators, is you get like just like a measurements and the state that was measured with the probability. And then you can just use, your SD, your Python, or whatever IDE you'd like to just analyze, like classically interpret the results and post-process them. Let's say, as a lot of algorithms, you just measure, you manipulate your state, your quantum state somehow, and use some interference to get to get something, and then you measure the zero state of the control qubit, and by measuring the zero state, you get some probability that tells you something that you wanted to know, like let's say some expectation value is hidden in this probability, or um or some like, or maybe the fidelity, the overlap between two, similarity between two different states is hidden in this probability. So generally you just measure a lot of times, a lot of shots, and you can manipulate your results to find out whatever you want, depending what, like which algorithm you used and what it should do, what this probability should you know, what's its meaning generally.
Yeah. Okay, that makes sense. So you mentioned that the maximum usage for, I guess, for free if you're an academic, is 28. Do you have like a record in your company of like the most number of qubits that someone internally has gotten to?
Like running on
Yeah. Simulated
um
wise, I should say.
layer wise. I'm not sure. Like our simulator, this is like a hard limit that it supports. We don't have like an internal simulator that can run more qubits. Than
Okay.
this. Generally like this is our highest simulator. We have another NVIDIA simulator that is like just NVIDIA GPUs. That's ours as well. We can give permission to use it to users if they request it. Generally, it goes up to I think 32 qubits, and generally, like I come from like classical simulated quantum systems, so I think like hard limits for systems that they're like state space, called Hilbert space, scales like exponentially with the number of let's say qubits, or let's say atoms, let's say particles. So I think like classically the like highest number you can get to is 35, 36 if you don't use some very very cutting edge methods that are not really like simulating 36. But generally, like it depends on the system as well. But generally, I'm not sure that Classiq can do much more. It's just like every, if you add one more atom or qubit, it scales exponentially. So it can like grow very fast at these sizes.
Do you happen to know what the limiter is? Is it the V, like the RAM on the graphics card, the RAM on the computer? Is it just processing time? It'll take longer, like too long.
Yeah, I think it's the RAM on, I think it's a RAM problem. Yeah, it's like,
Okay.
on your computer, you send it to like an HPC, it's a supercomputer in some HPC, but it gets really crazy really fast. The size of the files as well, but the RAM you need to do the calculations is getting crazy. I remember, in my research, I got to 32. And it wasn't like the highest number that anyone has gotten to in my system specifically as well. I did like a Rydberg atom system, like some basic. It's a basic layout of one of the quantum computers, called like a neutral atom quantum computers. So I had like a some limit of this theoretical model for this setup, and I got to 32, but I think you can get to more. And, you have all the matrix product states and everything, like very state-of-the-art techniques to simulate, like to get results, get what you want. If it's like ground state energy, or if it's propagating in time, like Hamiltonian simulation, like it's called in quantum computing. But like if you want to achieve what you want to do, you can get to I guess like up to 38, maybe 40 atoms. But this is like the top and scales like exponentially. So increasing it by one can be crazy, can get very crazy.
Yeah, I asked because I come from a high performance computing background, and so like it's always interesting to me like how scalability becomes an issue when you run a simulation and like you're like okay I want to have twice the resolution and now you're using four times as many processors and like it gets I always wondered like if I could get a faster computer, will I would ever be happy? Or am I just gonna like be running, twice as many time steps? Like is there a limit where I'm like, okay, this is fast enough to do all the phenomena that I want to see?
Um, like in when I'm in my research in physics, there's also always these finite size effects of systems. Like if they're finite sized, there's some effects, and you want to generally like look at the system like in the thermodynamical limit, meaning like you take the number of particles to infinity. And that's interesting to physicists. I'm a physicist, and my um, master's degree was in physics. So you'd like to, get to the like largest number possible, generally. You have your limitations, you have your HPC center of the university. It has some clusters, and these clusters have some limits as well, and this scales very fast. So like, getting from 32 to 33 to 34, let's say, being even, was crazy, crazy hard, very, very hard. And I needed to refactor my old code, like change my own code, my whole code, like from bottom to top in order to get from 28 to 32. So,
Yeah.
uh,
So I guess that's I guess the last HPC question.
mhm.
So let's say there was a NVIDIA came out with a breakthrough. They can, let's say, they quintupled the VRAM or like 10 times the VRAM on the graphics cards. Would your Classiq code be able to like handle it, or would you have to like rewrite it again to like if they suddenly said we can do 50 or 100?
It's a good question. Like how Classic works is generally we have a lot of constructs that and now like is like something nice. We have like auto on computation of some variables, meaning a way to free up memory as the circuit goes and reused by the same circuit as it continues. Um, so we came up with a lot of methods of uncomputation and things to make like circuits more efficient and the most efficient and optimal they could get. So generally, what Classic is great for is writing your algorithm and stating it in the abstraction level of an algorithm. And then Classic takes care of getting it to an optimal circuit. Now we're always improving how optimal the circuits get. And like as I've said, there's a new update with auto-on computation. We have, let's say, language constructs called within apply that generally implement some kind of procedure that is happens a lot in quantum computers. And generally, it also uncomputes ancilla auxiliary qubits that are used for some operations, so they can be used further along the way in the circuit. And that way you need less qubits generally. And this is something hard to do mathematically, And we want to do it, we want to give it to the users so they can have it as automatic as it gets. Like they don't have to think about how to do it because it just happens. And this will work for any quantum computers, for any cyber quantum computers. It's just like optimizing the circuit that goes into the quantum computer at the end.
Okay.
Hope you understood. I didn't lose you.
Yeah, yeah. So I guess last question. I've noticed that like okay, so quantum computing is kind of a new industry, at least like in the form of being an actual industry. And everyone seems to have their own path to it. You know, it's not like electrical engineering where you go to school for electrical engineering and then you get a job building motors. Like it's hard to make the jump. Would you mind sharing how you ended up at Classiq?
Yeah, of course, of course. I will start by saying you're right. It's kind of a like it's an interdisciplinary like kind of discipline, um, quantum computing, because it's like a mixture of of computer science and physics. And when physics becomes something more of an engineering manner, it becomes electrical engineering or mechanical. It depends on what part of physics we're talking about. But so yeah, so quantum computing is, I think, like it defies the like silo structure of universities. Because universities are very like, okay, you have physics and you have quantum computing and you have computer science, sorry, and you have electrical engineering, and they kind of like separated, at least in Israel. I'm seeing in Europe things are science, it's starting to change, but this is really a good question. And I would say that I will start by saying that I came from a background of physics, of condensed matter physics, did my master's in Ben-Gurion University, my bachelor's and master's, and I classically simulated like quantum systems, like the Rydberg atom approximation called PXP. It's effective Hamiltonian effective system, and I knew like quantum computing is kind of like the future, and I would like I was always like an idealist, I guess, and I wanted to be in something like to change the world. So quantum computing was generally like my dream job after the degree was going into some quantum computing startup because you don't have a lot of big quantum computing corporates yet. But I knew like I didn't know what are the chances because like okay, there's not a lot of quantum computing startups, but there's not a lot of like condensed matter physicists like as well, at least here. So I didn't know my chances, but and by chance like I got to hear about Classiq and I just like submitted my CV and they didn't have any opening. I just like heard about it from a friend who like gave me some connection, and they didn't have any opening. And a year afterwards, I just like checked the website. I saw some role that open, and I gave my CV again, and I somehow got accepted. And
Nice.
from there, I'm like a year in the company. I'm doing academic collaborations and engagements, meaning collaborating with academy and influencers and everything in between. And that's it. And if someone would like to get into the ecosystem, I would recommend um, I recommend like knowing computer science. I think a little bit better than physics because like the quantum side, I think is easier to comprehend if you have like the computer science side. Because quantum side, okay, it's kind of abstract, but in quantum computing, generally like less abstract, it's more practical because it's physical algorithms, and you can see how things happen. And as you know, quantum mechanics is generally linear algebra, uh, formulated differently. So I would recommend on pursuing a degree or a master in quantum in computer science, and then like taking some course in quantum computing or something, and if you have the time and effort and energy, do double degree with physics and computer science can be, I think, the best. Electrical engineering, of course, is welcome as well. I just like less have knowledge about like electrical engineering because I come from physics and a little bit of quantum of computer science.
Yeah, that makes sense. So you mentioned, yeah, so my friend and I started a not-for-profit. We are trying to build, and like this product's been out there for a while, but it's in like companies try to t sell it for like tens of thousands of dollars. And basically, what it is just an NMR quantum kit. Basically, I don't know if you're familiar with NMR,
Yeah.
nuclear magnetic resonance. Basically, it lets you talk to the protons in a bottle of water, so and act on them like if they were a qubit. So in some ways, you could call it a one qubit quantum computer, but that's that's on the edge,
Yeah.
um, hand wavy. Um, and yeah, basically, I was asking like we've been trying to find a place for this. I mean, obviously, there's the educational ecosystem because this thing will teach you, it'll teach you a lot of the hardware side. It'll teach you soldering. It'll teach you RF control, noise, op amps. But then also it'll teach you about the quantum side, T1, T2, spin echo, CPMG, XY8. That's other ways of saying dynamical decoupling schemes. And so um, but I have noticed that there's a lot of companies out there that like want to demo their products, but they don't have a good way to demo them because they basically either have to just like show a simulation or they have just like a simple resonator. Um, and this kind of holds for your company possibly, but also companies like quantum machines where they sell the box, but then they need someone else to have like the actual qubit, and they
Mhm.
can't like demo their box because there's nothing to demo on unless they like go through the trouble of connecting everything. And I think it's feasible to create a low cost product that is basically just like a simple qubit that lets whatever act on it and then like see the results.
Yeah, I totally agree with you. I think like as Classiq is also a software company and also like, in the with the perspective of, you writing the high level code and this engine doing the circuit, and we're not very coupled to hardware and these kinds of matters, I guess. So it will be a little hard to answer. I think like quantum machines will be a much better company to like, to have good answers for this than us. But I would say it does sound like something very, very, very nice to have at science experiments and even sold to I don't know if universities first degrees could be even like teach you a lot in first degrees. Um, like bachelor's, I mean, and high schools, of course, it can be very great. And asking some kind of like quantum machines about this is a great idea as well, or some kind of other hardware company or like somewhere between like I don't know how to call quantum machines. They're not very really hardware there. As you said, they give you like the tuning of the lasers and they need still in the qubits. I would ask them and I would generally um, reach out to I can maybe connect you to someone from quantum machines.
Okay, sure.
You can ask the question and it sounds really great. I just know that quantum machines are working with a lot of big companies, so somehow they did manage to demo without a bot, without like the qubits. I'm not sure how, but our demos are very coherent and nice because we run everything in our platform and it's very the flow is very um, coherent now after we did a lot of iterations. So.
Deterministic.
Yeah, if you'd like to like have another session, I could give you a demo that you can record it if you'd like sometime.
Yeah, that sounds interesting. Yeah. Or if you have like a video on YouTube, I can link to it. Um,
Yeah, yeah, we do have something. I'm not sure um how new it is because like things change all the times and we bring in new features and we change old features and we replicate them. So I need to find it, but generally, yeah, you should find something on our YouTube channel, Classiq YouTube channel.
cool. Thank you, Adam Gitter. Hopefully I pronounced that correctly.
Yeah.
From Classiq. It's always tricky with companies that have a Q at the end. You're like not sure if it's like Classiq Q or like Spin Q, but it seems like it's just Classiq, right?
Yeah, yeah. A lot of people call it like with a French accent, like classique. No, no, it's classic.
Yeah.
Yeah, yeah.
Okay. Well, yeah. Well, thank you. Thanks for taking time to talk to us.
Sure, sure. Okay, so we'll stay in touch. It
Yeah,
was
of
great.
course.
See you. Bye bye.